Been a little low today. All right, we're recording. So, good morning, everybody. Welcome back to Math 115. I will get the iPad into the meeting and then share the screen. Okay. One second. Whew, almost forgot to plug in the thing that makes that god-awful sound stop. All right. So last lecture for the week. I hope everybody's ready to have a weekend. Speaking of the weekend, this coming Monday is going to be President's Day, okay, which I guess is a holiday which you're supposed to get off. So there's going to be no class on this coming Monday, February 15th. Okay, so there's not going to be any synchronous class. I'm not going to post any videos or anything. You guys should just take that time to rest and relax and catch up on schoolwork if you need to do that. And yeah, so that's your day. So I'm not going to do anything for that. Let's see, what else? Exit slips. Okay, I put this on the announcements because there are some students who haven't been completing the exit slips, and that confuses me because they're worth 7% of your final grade. And I'll omit, I can't remember what's in the syllabus, but I think I'll omit like 2 exit slips. So if you miss a couple days of classes, no problem. But if you miss like 10 exit slips in a row, that is going to affect your grade significantly. So just keep an eye out for those exit slips and make sure that you're keeping up with those. I think the best way to do it would just be to attend class synchronously, or just whenever you watch the video, just immediately go do the exit slip. Or you could even fill out the exit slip while you're doing the class. I mean, that might kind of distract you, but I think it's just best if you can do it as fast as possible so that it's fresh in your mind, and then you don't have to worry about remembering to do it when it's like, you know, Tuesday night and you're like, oh crap, I forgot to do the exit slip from 1 week ago today. So yeah, that's exit slips. Grades in Blackboard are totally up to date. So just a reminder, when you look at your grade on Blackboard, all I'm going to post is your grade for the assignment, okay? And that's not necessarily going to correspond to like your grade in the class, because the grades for all of your assignments and exams are going to be weighted according to the setup which is on the syllabus. So do be careful looking at Blackboard. Don't think that that, you know, is going to immediately represent your actual grade in the class. It doesn't really make sense to calculate your grade before the end of the semester anyway. But keep an eye on it. Keep an eye on your homework percentage. Keep an eye on your exam percentage. And also make sure that all of your assignment grades match up with what you see on Pearson, because you can check on Pearson and see your grade book and see that. Check and make sure that your grade matches up in Blackboard as well. And look over your exam and make sure that I tallied up all your points right and gave you the right score. And if you see any exit slips, which you did, but somehow you got a 0, just email me about any of these issues, and I'll look into them and we'll get them sorted out. Okay. I think that's all I have administrative wise. Anybody have any questions or comments about those kind of aspects of the course? Okay, seems like not, so we will get started. Okay, so before we start with the new material, let me go back and just review really quickly what we learned last time. So last time, here we are, we started with this algorithm for how we divide polynomials, okay? And we had this kind of overarching equation, f of x is equal to d of x times q of x, okay? And if we can write an equation like that, then we say that d of x is a factor of f of x, okay? If we can take it out of f of x, basically, and we get another polynomial, then we say that we've basically evenly divided f of x by d of x. It came out very nicely, and we had no remainder, okay? So that's what it meant for d to be a divisor, or a factor of f of x, okay? And we called q of x the quotient. Okay, but sometimes we realize, okay, just like with regular numbers, sometimes a divisor doesn't divide out nice and perfectly from our dividend. Okay, in that case, we have this equation where we write f of x is equal to the divisor times the quotient, but we have this pesky remainder term out back. Okay, so sometimes we get a remainder. And then basically the rest of the class we spent talking about how to do long division. And it was a very long process. And it was sort of extra long because I was explaining all of these steps as we went along. But hopefully it wasn't too confusing. Basically, we just want to continue after we do step 1 and step 2 and get the division set up. We just want to repeat step 3 and 4 over and over again until we get a remainder term which has degree which is smaller than the degree of our divisor. And once we get to that, we call that our r of x times d of x. So in this case, we went all the way to x plus 2, and we noticed that had degree smaller than our divisor. And so we just write that the whole thing is equal to the quotient, and then we just take whatever we have left at the very end and we divide it by our divisor, and we call this term our remainder. Okay? So that was long division. And then we did another example. This is some office hours stuff that I did. By the way, this is all recorded, so if you want to see some extra stuff about long division, you can go to the recording and skip to the end of class. I worked with a student on some more long division stuff. Okay, that's still that. All right, and then this was really the most important thing that we learned was what is long division actually useful for. And it's useful for factoring polynomials which are not just quadratic, but they might be cubic or quartic or quintic or any higher order polynomial. Okay, and the way we did that was just by plugging in different values of x and seeing if we can find one which gives us a 0. Okay, and if we're able to do that, then we know that x minus that number will be a factor, and so we just apply long division to divide it out. Okay, so I noticed that 1 was a factor of this polynomial, so I divided out the factor x minus 1, and that gave me, instead of a quartic polynomial, in the end, I wound up with this x minus 1 pulled out, and my remainder here, or my quotient, excuse me, was just a cubic. Okay, so now I'm going to apply the same process to this thing and guess another root of that one. Okay, it looks like -1 will work. So I would then try to divide out -1 from this guy and rewrite this thing as x plus 1 times something here, which is going to be quadratic. Okay, and then I can just factor this one. Okay, so I'm not going to do all that today because it's just repeating the same step that I've already done. But that's how we factor. That's how we factor these higher order polynomials, which is actually a fairly useful thing to know how to do if you're going to move forward with more math. Okay, so that's all we covered last time. If you want to see me maybe finish this example, we could do it after class. Oh yeah, one more announcement actually, having to do about exit slips. I noticed that a lot of students write on their exit slips statements that say something like, I want to see more examples of this particular problem that we did in class today. And unfortunately, since I have to move forward with the material, and right now the material is kind of coming at a pretty quick pace, there's not really going to be time for me to do more of these examples during lecture. But if you guys come to office hours, I just have 3 hours of office hours per week. I will work example after example after example with you for hours on end and do literally anything that you guys want me to do during those office hours. And most of the time, nobody really shows up. So take advantage of those. Okay. That's a brief aside. Now, today we're going to talk about rational functions. Okay. We're going to talk about rational functions. So what is a rational function? So as usual, we'll start with our main setup. We have a function f of x, and we say that it's equal to n of x divided by d of x. Here, n for numerator. And this time d for denominator. Okay, and we have that n and d are polynomial functions. Okay, so rational function, we have a polynomial divided by a polynomial. Okay. All right, so let's talk about the domain really quickly. And this is the one place where rational functions kind of differ from our polynomial functions, or this is one of the places where we differ from our polynomial functions. Because while polynomial functions, remember we said that the domain of a polynomial is just all real numbers. Well, the domain of a rational function is again going to be all real numbers, except we need to throw out any x values that cause the denominator to be equal to 0. Okay, so for example, if f of x was equal to x minus 2 divided by x minus 1, the domain would be all real numbers except x equals 1. You can't use 1. So we would write that as negative infinity comma 1 union 1 comma infinity. All right, so that's really the only thing we have to worry about for rational functions. We need to make sure that the denominator is not 0. Okay. So the following few pages are going to describe the graph of a rational function. Okay, we're going to learn all about how to graph rational functions, and there's going to be a lot of things to consider. And then finally, we're going to sketch the graph of a rational function using all of the tools that we learned today. Okay, so that's where we're headed. And the first thing that we have to talk about is vertical asymptotes. Okay, I'll describe what a vertical asymptote is. So first we'll say when we're going to have one. We're going to have a vertical asymptote at x equals a if f of x goes to positive infinity or negative infinity as x goes to, now this is new notation here. A, sometimes I will say A from the left or from the right. Right. Okay, and what that means is I let my x values, okay, so if x goes to A from the right, I let my x values become arbitrarily close to A, but larger than A. Okay, so x goes to A, but x is larger than A. Okay, that's what is happening. And if I do x goes to A from the left, what I mean is that I let the x values become arbitrarily close to A, but x should be less than A. So x goes to A, and x is less than A. Okay, this is what this notation means. Okay, so f of x has a vertical asymptote if the height of our function is becoming unbounded, either in a negative way or a positive way, when the x values that we're plugging in get really close to this value A. Okay, that's what a vertical asymptote is. So for example, we could have f of x equals 1 over x. Okay, and let me ask you, are there any vertical asymptotes x equals A for this function? Do we have any places on this graph where the height of the graph is going to infinity? What do we think? Okay, answer of yes. You want to go for gold and tell me where that's going to happen? Can you describe the x value where that's going to happen? Taking across the origin or up one. Yeah, so it's going to happen basically near the origin. You're right. Okay, so here's what the graph of 1 over x looks like. If we were to graph this function, it looks, it's not very good. It looks crazy like this. It gets huge right here, and then on the other side, it looks crazy like this. It's going way, way down. Okay? The reason is, if we were to take a sequence of values here, say like 1, and then like, I don't know, 1/2, and then something like 1/4, and then like 1/8, and then something like ... and then we take something like 1 over 1 million. I don't know if that's 1 million or not. Then the values of f of x are going to be 1, and then at 1 divided by 1/2, we would get 2, and then at 1 divided by 1/4, we would get 4, and then 1 divided by 1 over 1 million would be equal to 1 million, right? Okay, so the point is, as the x values get really, really close to 0 here, the graph of our function is becoming unbelievably tall. Okay? In fact, I can make it as tall as I want. You give me a height, and I'll tell you the x value that causes the function to be that high. for any height. You could give me like a Google. I think it's spelled Google. That's like one with like I don't know, a billion zeros or something. No, that's too crazy. It's like 100 zeros. And that's going to happen when x is equal to 1 over a Google. Right? Then 1 over a Google is a Google. Okay, so the point here is that the graph of our function is becoming as tall as you can imagine as the x value becomes very, very close to 0. Okay? But there's something important to notice, which is that this is only happening. We only have f of x becoming unbelievably tall when we go to 0 from the right. If we go to 0 from the left, instead of becoming unbelievably tall, it's becoming unbelievably, I don't know, low, I guess. Okay, so the way we would write this is we would say f of x goes to infinity as x goes to a from the, from the right. Okay, so I'm going to put a plus here. And then we would say f of x goes to negative infinity as x goes to a from the left. Okay? And we only need one of these things to be true. Okay, we just need f of x going to some kind of infinity as x approaches a, either from the left or from the right. Okay, if we have any kind of blow up happening, we call this a vertical asymptote. Okay, so f of x does have a vertical asymptote. It has a vertical asymptote at x equals 0. Okay. One more thing that I want to really briefly mention is I'm going to start sort of introducing a little bit of this notation. Okay. When I write, man, I didn't leave myself very much space here. When I write this stuff, sometimes instead of that, I'm going to write something like this. Limit as x goes to a from the right of f of x equals infinity. Okay, I'm just going to burst everyone's bubble now and start introducing that notation because it's way more descriptive and faster to write. And then the other one is lim as x goes to a from the left of f of x is equal to negative infinity. What this is saying is as the x values become very, very close to a, but smaller than a, the value of f of x is getting very, very close to the value negative infinity. Okay, that is what this notation means, and it means the exact same thing as what we wrote above. Okay, it's just a slightly different way of writing it. Okay, so when are we going to have a vertical asymptote? We're going to have it whenever the denominator's 0 and the numerator is not 0. Okay, so if we have the denominator equal to 0 at a given point x, and we also know that the numerator is not 0 at that point x, we're going to have a vertical asymptote there. Okay? We'll talk about what happens if we have both of these two things equal to 0. If we have both equal to 0, we don't know what's going on yet. Okay, any questions about the vertical asymptote? All right. Well, now we'll talk about horizontal asymptotes. Okay, so horizontal asymptotes, f of x is going to have a horizontal asymptote at a horizontal line y equals k if the limit as x goes to infinity of f of x is equal to k. Okay, so here's k, and here's the line. Why don't I just draw it in? Here's the line y equals k. Okay, and so what do these statements say? It says that the limit as x goes to infinity, so that means as our x values go out, out, out to the right forever and ever and ever, the height of our function is becoming really close to this height k. That's what this notation says. And then this other one says, or we have the limit as x goes to negative infinity of f of x. And this shouldn't say negative k, this should just say k as well. So the limit as x goes to negative infinity of f of x is just equal to k, which is to say that if we take x values which go very, very far out to the left, then the height of our function becomes really, really close to this height k. Okay, so I'm going to draw a function here which satisfies these properties. And I'm going to make a point, which is that what's happening with the function in the middle doesn't matter. Okay, this is kind of like the end term behavior again, where this is describing something about what's happening to the height of the function really, really far away. Okay, we're not really saying anything about what's happening in this middle region. So f of x might look really, really crazy. I don't know, doing something really nuts. But what we're saying is that after a really long time, this graph is getting very close to y equals k. And same thing if we say in the left direction, if we say limit as x goes to negative infinity of f of x equals k, we're saying that after a really long time, the height of our function is getting arbitrarily close to this line y equals k. Okay, but we could be doing something crazy in the middle. So this is what it means for f of x to have a horizontal asymptote at y equals k. And now let's talk about when it's going to happen. Okay, and we have a couple of rules for this. Okay, here they are. So if we have some function f of x, it's a rational function, so we can write the top and bottom in terms of their polynomial expansion. Right? This is just standard form to say that the leading term of the numerator is an times x to the n, and the leading term of the denominator is bm times x to the power m, where these powers n and m might be the same or might be different. Okay, so this is just a general notation to say that we have two polynomials being divided by one another, not necessarily the same degree. And what these rules say is that based on the difference in the degree of the numerator and the denominator, we are going to have some rules about whether or not we have a horizontal asymptote. Okay, so what does the first rule say? It says if the degree of the numerator is less than the degree of the denominator, then y equals 0 is the horizontal asymptote. Okay, for example, f of x equals x over x squared plus 1. Something like this would satisfy the first property because the power n in the numerator is 1 and the power m in the denominator is 2. So since 2 is larger than 1, we would say that y equals 0 is the horizontal asymptote, which is just to say that basically as x becomes really, really big, this numerator is going to be like super small compared to the denominator, right? If you look at the difference between a number and its square, 1 and 1, 2 and 4, 3 and 9, 4 and 16, I don't know, 9 and 81, 10 and 100. This is like saying that the difference between these two numbers as x gets larger and larger and larger is going to be getting wider and wider, which is to say that this denominator is kind of getting really big before our numerator is getting very big. Okay? So in that case, the fraction is going to be getting close to 0, since a number, if we have a fraction and the denominator is way, way bigger than the numerator, that's like saying that the number is close to 0. So the height of our function is converging to y equals 0. Okay? So that's what happens if the denominator has a higher power. The next rule says what happens if the numerator and the denominator have the same power. Okay? So if the numerator and denominator have the same exact power, then the horizontal asymptote is going to be given by the ratio of these terms, an and bm. Okay? We just take the leading coefficient of the numerator, divide it by the leading coefficient of the denominator, and that's going to be our horizontal asymptote. Okay? And finally, if n is larger than m, then we don't get any horizontal asymptotes. The reason being, if we had something like f of x equals x squared plus 1 over x, then what's happening is this thing is going to infinity faster than the denominator, which means that the height of our function is going to be unbounded. Okay? So we're not going to have a horizontal asymptote because the height of our function is not really coming closer and closer to a finite value. It's going to infinity. Okay, so if the numerator power outweighs the denominator, then we don't get any horizontal asymptotes. Okay, so let's see this example here. Here we have f of x is a function, f of x equals 3x cubed plus 21x divided by 2x cubed minus 6. And we want to determine where are the asymptotes. Or is there a horizontal asymptote? Okay, what do we think? Do we think that this function is going to have a horizontal asymptote? A few answers coming in. Yes, even got an answer for where it's going to be. Okay, what do we need to look at here? What we need to look at is the power of each of these, numerator and the denominator. It looks like the power of the numerator is 3, and the power of the denominator is going to be 3. So those two powers are equal to one another. So we're going to be in this middle case here, right? Okay. We have n is equal to m. Okay, and if n is equal to m, then we do have a horizontal asymptote. In fact, we even know what it's going to be. We know that the horizontal asymptote is going to be the coefficient which is attached to the leading term in the numerator divided by the coefficient which is attached to the leading term in the denominator. In our case, those coefficients are 3, because that's what we have with the highest power of x, and 2, which is what we have with the highest power of x in the denominator. Okay, so in this case, we are going to have a horizontal asymptote at y equals 3/2. Okay, at y equals 3/2. That's where we're going to get it. Okay, so all we have to do is just kind of compare the largest power of x in the numerator and the largest power of x in the denominator, and depending on how those two numbers are related, we're going to either get y equals 0 to be the horizontal asymptote, or we'll get that if they're if the powers are equal, we'll have this situation where we just divide the coefficients. Or if the power in the numerator is larger, then we just say that there's no horizontal asymptotes. Okay? So just to reiterate here, what we're comparing initially to determine whether or not we have a horizontal asymptote is these powers of x, the largest power of x, okay? So in this case, I might have misled some students by saying, well, we have a 3 here and a 2 here, so the number on top is bigger, so we're going to be in this case, right? But that's misleading reasoning, because n and m here are describing the powers n and m on our x values here. Okay? So that's what's going on with the horizontal asymptote rules. Any questions about that? Is that clear? Or could it bear more explaining? What is the significance of the n and the m next to the coefficients? That's a great question. So these n and m are just a subscript, okay? So they're not like a power. So when I write x to the n, I'm saying x times x times x dot 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 times x, where I do this multiplication n times. Okay, when I say an, I'm referring to the nth term in a sequence of numbers. For example, 3, 5, 7, 17, -2, -1. These might be the numbers a0, a1, a2, a3, a4, dot, dot, dot. Okay, so I have a sequence of numbers. So the reason I put an and bm here is because in a polynomial, we're going to have something like x cubed plus something x squared plus something x plus a number, okay? And the point is that I can choose a sequence a0, a1, a2, a3, a4, dot, 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 to fill in these gaps here, okay? So I can describe the collection of all these coefficients by a sequence, okay? So I could say that, okay, I see a3 is 17, so I'm going to put 17 right here. I see that a2 is 7, so I'm going to put a 7 with the x squared. I see that a1 is 5, so I'm going to put a 5 with this x. And I see that a0 is 3, so that's going to be my constant coefficient. So that is the significance of this a with a subscript. I'm talking about just some number, and I'm talking about the nth number in a list of numbers. Okay? Does that clear things up, Sam? Okay, cool. Yeah, so this is not anything special like I'm doing a power or anything. When I put the subscript, it's just to describe the place in the sequence. I'm saying it's the nth number in the sequence or the mth number in the sequence. Okay, so that's how that works. Okay, for the sake of time, I think we've got to move on here and talk about holes. Okay, remember at the end, we're going to see how to do all of this stuff together. So we're going to come back to this horizontal asymptote stuff. So what is a hole? Well, f of x is going to have a hole at a value x for which n of x and d of x are both equal to 0. Okay, so remember, we said that we would have a vertical asymptote if d of x was equal to 0 and n of x was not equal to 0. But we get a hole if d of x equals 0 and n of x is also equal to 0. Okay, so that's the difference between these two things. Okay, and here's how it looks in practice. So we might have some rational function like this, x squared minus 9 divided by x minus 3. And we can see that there's going to be a value of x such that if we plug it in, we're going to get 0 on the top and the bottom at the same time, right? It's x equals 3. That'll give us x squared minus 9 equals 9 minus 9 equals 0. And also, it'll give us 3x minus 3 equals 3 minus 3 equals 0. So this is telling us that we are going to have a hole at x equals 3. Okay, and here's why. The reason is, if we have a 0, a number which is a 0 of the numerator and a 0 of the denominator, then that means that x minus that number is a factor of the numerator and the denominator. It's trivially a factor of the denominator since it's already the entire thing. But the top can also be factored as x minus 3 times x plus 3. And if we have a factor in the numerator and the denominator, then we can cancel. Okay? And we will get that this function is equal to x plus 3 provided, and I'm going to put this in big lettering, provided that x is not equal to 3. If x is equal to 3, then the function itself is not even defined because we would be dividing 0 by 0, and that just doesn't even make any sense. But as long as x is not equal to 3, we can do this division like this and cancel these things out, and we're just going to get x plus 3. So what does the graph of this function look like, you might ask? Well, it's just going to look like the graph of x plus 3 with one small catch. The small catch is that when x is equal to 3, our function is not even defined. So we put a hole here. In fact, I don't even want to draw this line which goes all the way through here. I'm going to draw something like this. Okay, we have this line which looks like y equals x plus 3 everywhere except for when x is equal to 3. When x is equal to 3, f of x is equal to 0 over 0 is undefined. Okay? It's like asking, you know, if I have 0 slices of pizza and I divide them up among my 0 best friends, how many slices of pizza does every friend get? It's nonsensical, right? Okay, so we say it's undefined at that point. So that's why we draw a hole. Okay, so that's just going to happen anytime that we have a common 0 between the numerator and the denominator, because a common 0 means we have a common factor, means we can play this canceling game, and then everything's going to be fine except for at that one point. So that is about holes in the graph of rational functions. Questions for the holes section? Okay, seems like not. So we'll keep trucking. This might be the last, no, second to last thing, I think. Yeah, second to last thing before we're ready to actually graph go to the big leagues and graph a real rational function. The last thing second to last thing I want to talk about is the zeros of a rational function. Okay, so where does the rational function cross the x-axis? Okay, where is this going to cross the x-axis? Well, if I have a number, which is a fraction, if I have a over b, and b is not equal to 0, when is this fraction going to be equal to 0? If I have blank over 6, or blank over 3, or blank over 4. Now I want to say that these are all equal to 0. What does the numerator have to be? 0, right? So this is just to say that a fraction is going to be 0 if the numerator is 0 and the denominator is not 0. Okay? So we already described what happens when the denominator is 0 and the numerator is not 0. That was a vertical asymptote. We already talked about what happens when they're both 0. Okay? That was when we get a whole. And now we're going to say what happens when the numerator is 0, but the denominator is not 0. And in that case, we get a 0 for the function, and it's going to pass. It's either going to pass through the x-axis or it's going to touch the x-axis and bounce off. Okay? So for example, f of x equals x plus 1 divided by x plus 2 might look like the following. Well, we know we have a vertical asymptote at x plus 2, and we know that immediately to the left of that we would be having something which is a little bit less than 2. The numerator is going to be positive, the denominator is going to be positive. We're going to be going up to positive infinity. So it's going to look something like this, very close, and something like this, really far down there on that side. But we can see that when x is equal to 1, we're going to have a 0. So it's going to pass through this point here. Wait a second, x goes to infinity, this thing goes to 1. How are we having a 0 there? Oh, what am I doing? Sorry. Get out of here. Okay, what have I done? I put the zeros on the wrong side. We should have the zeros on the left side, right? At -1 and -2. So we have a 0 at -2, and if we're a little bit to the left of -2, then the top is definitely negative, and the denominator will be negative as well. So we're going up to positive infinity, and then again on the left-hand side, we'll be going up. On the right-hand side, we'll be going down. It'll look more like this. Oops. It'll look like, God, I cannot draw for my life. Okay, we come in and then we go way, way down. Okay, so this one's going to look like this. And by the way, this line here, this orange line, is the line y equals 1. Because if I were to look at the coefficients on the terms in the top and bottom, since we have the same power on the top and bottom, we know we're going to have a y, or a horizontal asymptote, at the value, which is the fraction described by these coefficients. And the coefficient on x in the top and the bottom is both 1. So we do 1 divided by 1 and get 1. Okay? And this is what this is going to look like. Okay? So the whole point of this is really just to drive home the fact that we're going to pass through the x-axis at this point here when x is equal to -1. X equals -1 implies that the numerator equals 0 and the denominator equals 1, which is not equal to 0. That's the main thing that we care about. So we have numerator 0, denominator not 0. That is where we are going to be touching the x-axis. Okay, sorry, I got really confused there for a second and put my zeros on the wrong side of the graph. Okay, questions about zeros of rational functions? Okay, I swear this is all coming to a head soon. Can there be multiple zeros? Absolutely. We could have multiple zeros if the numerator was something like, if we had a function like f of x equals, I don't know, x plus 3 times x plus 2 times x plus, and the denominator was, I don't know, x plus 72. In this case, we're going to have a 0 at x equals -3, a 0 at x equals -2, and a 0 at x equals -1. So yes, we absolutely can have multiple zeros. Okay. So now let's talk about what's happening to a function, a rational function, basically near one of its vertical asymptotes. Okay, so I kind of glossed over this when I talked about the vertical asymptotes. I said we're going to have a vertical asymptote if the function is becoming unbounded near an x value. And this is going to describe to you, if we have a vertical asymptote, how do we know what's happening on the left and right? Okay, because if we have a vertical asymptote, say we have a vertical asymptote at this value here, we want to know whether our function looks like, does it look like this, where we blow up to infinity on both sides? Or does it look like this, where we blow up to -infinity on both sides? Or are we going to have mixed behavior, where we have blowing up to infinity on the left, -infinity on the left, and positive infinity on the right? Or are we going to have blowing up to, the last one would be, are we going to have, oh, I already used purple. Are we going to have blowing up to positive infinity on this side and negative infinity on this side? Okay, so we have all these different options of what could be happening here. Let's see here. Something is wrong. Okay, I'm in trouble now. I've done something bad. Well, I haven't done something bad per se, but I've done something which is... Oh, God, misleading is what I've done. I've misled people. Okay. Let me add a page here and describe this properly. I need to add a couple more cases. Luckily, I can do that pretty quickly on the iPad. Okay, give me 2 seconds to fix this, and then we'll go forward. and then this will be m is even. And then this will be to the power m, to the power m, to the power m. This will be to the power m. And then this will be positive if we have an even. Goes to infinity. Negative infinity, and this one will be positive infinity. And then all of these, we just need to make sure we're doing to the m. Okay. Well, I've covered my butt now, at the possible expense of making this section really, really long. Okay, but at least it'll be completely general, and we're going to wind up seeing, basically, when we're going to have each of these either red, purple, green, or brown cases. Okay? So here's the deal. We have some function f of x, and we can express it as n of x divided by x minus a to the power m times q of x. Okay? So what this is saying is that n of a is not equal to 0. Okay, so x minus a is not a factor of x minus a, not a factor of n or q. Okay, so in other words, we've fully factored out all powers of x minus a, which is possible to be factored out of the denominator, and we say that x minus a is not a factor of the numerator, so we're not going to be worrying about wholes. Okay, in this case, we check the sign. Since we know that n of a is not equal to 0 and q of a is not equal to 0, we check what is the sign of n of a divided by q of a, and I call that number a. Okay? Then, if a is larger than 0 and m is an odd integer, okay, the first thing to realize is that odd is going to give us one of these situations, which is either green or red in this graph here. By the way, if you're colorblind and this presents a problem for you, please submit an anonymous survey and tell me that this is not working for you. No, not red. It should be green or brown. Green or brown, okay? So we're going to wind up in one of these situations where we have sort of opposite behavior on both sides of the asymptote. Okay, one side's going to go to negative infinity and one side is going to go to positive infinity. And the way we distinguish between which side is going to plus infinity and which side is going to negative infinity is by checking the sign of this value a. Okay? Okay, so if a is positive, then what is happening when we approach a from the left? Okay, so when we approach a from the left, x will be a number which is less than a. If we take a number which is less than a and we subtract a from it, then this number, x minus a, will be a negative number, which is very small. And then we take it to an odd power. If we take a negative number to an odd power, we're going to get a negative number still. So we're going to take a number a, which we know is larger than 0, and we divide it by a small negative number. Okay, if we take a positive number and divide it by an incredibly small negative number, we're going to get an incredibly large negative number. So that's how this is working. Okay, now let's check the other one. If a is positive and we take x goes to a from the right, well, a is less than x now, so this will be a positive number. We take a positive number to an odd power, we still have a positive number. So we have a positive number on top being divided by an extremely small positive number on the bottom. That's going to give us an extremely large number. Okay. So this whole case is, on the left, we're going to negative infinity. On the right, we're going to positive infinity. This whole case is the green case. Okay. And then likewise, if we have a is less than 0, we're going to be in the brown case. Okay, here's why. In this case, a is a negative number. So if we take x is slightly less than a, then this will be a very small negative number. So we take a negative number, divide by something really small, which is negative. Take a negative divided by a negative, we get a positive. And since we're dividing by something extremely small, we get something which is extremely big. So this is the brown case. And that's when we have opposite behavior. So we're going to have opposite behavior whenever the multiplicity of the factor x minus a in the denominator is odd. Okay. Now, if we have the opposite happening, okay, so if we have m is an even number, then what is happening? Okay, so first let's look at when a is larger than 0. Okay. What's going to happen when m is an even number is it's not really going to matter whether we are approaching from the left or the right, because this number, be it negative or be it positive, it doesn't matter because we're taking it to the mth power. Okay, when we take it to the mth power, we are going to get a positive number because m is an even integer. We take anything to an even power, we get a positive number. Okay. So in both cases, we have a positive a, and then the denominator will be a small positive number. So we're going to get something which is an extremely large positive number. So in this case, we have the situation up here, which is in red. Okay, we have both of these guys going up to positive infinity. So this is the red case. And then if a is less than 0, well, if we take a is less than 0, so a is negative, and the bottom is positive and very, very small. When we take a negative number divided by a positive number, it's still negative, but it's going to be really big because we're dividing by something incredibly small. Okay, so this final case is the one where both of them are going down. So it's going to be the purple one. So I'll switch to my purple. And that's what's going on here. Actually, I think I used the other purple. Okay, so each of these cases here correspond to this diagram up in the top right here, okay? So they're going to tell us whether we have up on the left and down on the right, down on the left and up on the right, or up on both sides or down on both sides. So this is just describing the behavior of f of x near an asymptote. Okay, so you can always return to this diagram here, but if you ever wind up in trouble and you have an asymptote, okay, so you have an asymptote at some point, and you know where the value is, just check the value of f of a plus 0.0001 by hand. If you get something really big, then you know you're going up. And then likewise on this other side, a minus 0.0001, okay? So that's the long way of doing things. would be, you'd be going down like that. Okay, so if you have something really big, then we get this kind of picture. And if we have something really negative, then we would have something like this. So that's how you can do it in practice if you don't want to use this entire process. Although this process is completely comprehensive. It'll tell you exactly what it should look like. Okay, dare I ask, are there questions about this vertical asymptote behavior depending on the value of m being even or odd, and depending on the value of n of a divided by q of a being positive or negative? Let me ask another question. As I was going through this, did this logically make sense to you guys, or was this kind of too abstract? It's okay if it was too abstract. Okay, I need to see it worked out to make sense. Okay. We can do that. Definitely need more practice. Okay, then let's not waste any time. Let's actually do one. Okay. So now we have basically everything we need to sketch the graph of a rational function. So here's one, which we can sketch the graph of. And I've listed basically everything here that we need to worry about. Okay, we need to check, are there zeros? Are there horizontal asymptotes? Are there vertical asymptotes? And are there holes? Okay. And then we'll worry about actually graphing it. So first thing I'm going to do is factor this completely. That's going to make it easy to see what's going on. The top looks like it factors, this is 2 times x squared minus 1, which would be the same as 2 times x minus 1 times x plus 1. That's how the top factors. And the denominator factors as x plus 3 times x minus 3. So remember, the zeros happen when the numerator equals 0, denominator not equal to 0. So that's going to happen when x is equal to positive 1 or x is equal to negative 1. Okay, so we have zeros there. Now let's check the horizontal asymptote. Okay, the horizontal asymptote had to do with the powers of the numerator and the denominator. Here the power of our numerator is equal to 2. The power of our denominator is equal to 2. These two things are equal. Implies the horizontal asymptote is going to be an over bn, which in our case is 2 divided by 1, where this 2 came from here and the 1 came from here. So y equals 2 is a horizontal asymptote. Now we check for vertical asymptotes. Vertical asymptotes are going to happen when n is not equal to 0, but d is equal to 0. Oops. So that's going to happen at x equals 3 and x equals negative 3. Okay, because the top is not going to be 0 at either of those numbers, since x plus 3 and x minus 3 is not a factor of the numerator. Okay, and let's hold off for the time being on describing the behavior near those asymptotes. Okay, so now we check the holes. Are there any holes? Holes is when the n is equal to 0 and d is equal to 0. Well, since the numerator and the denominator do not have any common factors, we don't have to worry about holes. Okay, so now using all of this information that I've written down here, I'm going to start graphing this rational function. So I'm going to start by putting the zeros on the graph. I know I have a 0 at x equals 1 and x equals negative 1. So let's start graphing. I know I have a 0 at x equals negative 1 and a 0 at x equals positive 1. So I pass through the x-axis at those 2 points. Next up, I know I have a horizontal asymptote at y equals 2. So I'm going to draw that in here. Oh, come on. Behave. This is y equals 2. And I know that very far away, okay, very far away, I'm going to be getting close to that thing. Okay, I'm going to refrain from drawing the graph for the time being. All right, then vertical asymptotes. I have one at x equals 3 and x equals negative 3. So let's draw what it looks like. Maybe I'll use red for the vertical asymptotes. I'm going to draw these with a dashed line. Okay, so these are my vertical asymptotes. And I don't have any holes. Okay, so what remains to do basically here is to check the behavior of our vertical asymptotes. Okay, so first of all, check the a value. So we'll do x equals positive 3 first. Okay, so we're going to worry about this one, this asymptote here. Well, the denominator is going to be, we have the numerator is going to be n of 3. We want to check what that is. That's going to be 2 times 3 minus 1 times 3 plus 1 is going to be equal to 2 times 2 times 4 is 16. And q of 3 is going to be what we get when we plug in to the factor which does not correspond to the asymptote at x equals to 3. So the denominator here, which is not our factor, is just x plus 3. So if I plug into q of 3, in this case, it's going to be equal to 3 plus 3 is equal to 6. And we know that m is odd. Altogether, this is telling us from before that what? We have a greater than 0 and m is odd. So let's go back. If we have a greater than 0 and m is odd, we're going to be in the green situation, which means we're going to be going down to negative infinity on the left side and up to positive infinity on the right side. So what the heck is this going to look like? We're going to be going down to negative infinity on the left side and up to positive infinity on the right side. Okay, Now I check the other side. If x is equal to -3, then n of 3 is -3 is going to be equal to 2 times -3 minus 1 times -3 plus 1 is going to be 2 times -4 times -2. Still get a larger than 0. Wait, do we? We get a larger than 0. No, something's wrong. Oh, duh, because q. But q is the factor which is not corresponding to x plus 3. So q of -3 is corresponding to the factor -3 minus 3 is equal to -6. So we get 16 over -6, and that's telling us that a is going to be less than 0 and m is odd. Therefore, going way back up to our thing, I know I'm over time, sorry. We're going to have down behavior on the right side and up behavior on the left side. So what does it look like? We can fill in this thing. It's going to look something like this. And on the left side, we are going to have up behavior. So finally, we have our graph here of our function. All right, I think that's all we have time for today. Are there any questions about how I made this graph here? Scroll down just a bit. Yeah, of course. Sorry. So this, remember, implied that we get the brown behavior. And this implied that we get the green behavior. Okay, well, if there's no questions, then we're done for today. Sorry for keeping you guys a little bit over. If anybody wants to see maybe one more example, you can stick around after class. Otherwise, today's over. Have a nice weekend, and don't forget there's no class on Monday. Does anybody want to stay after and see one more example? Yep, have a good weekend, Heidi. Can I make another exam? How do you mean?
Example, teacher, I'm sorry.
Oh, yeah, sure. Let's do one more example. Okay, let's try this one. Okay. In fact, why don't I even just make this 2x cubed? 2x here. Why don't I even make it -2x minus 4? No, that doesn't work. -2x minus 6. Okay, so let's try this one. So first of all, we can see that we don't have any common zeros between the numerator and the denominator. This tells us we have no holes. Let's check the horizontal asymptote. If we were going to multiply all this stuff out, we would get that the leading term would be what we get from doing the f step in the FOIL step. We've got negative 2x squared over x squared is the leading terms. And we would notice that this 2 here and this 2 here have the same power. So we are going to have a horizontal asymptote. And it's going to happen when y is equal to negative 2 divided by 1 equals negative 2. We're going to have vertical asymptotes at x equals, well, just at x equals 1. Right? Because that's the only place where the denominator would be 0 and the numerator would not be 0. Okay, and the zeros of this function
6 and 2 and minus 2.
We'll have at minus 2 and not 6, but we want to think about what could we plug in for x here that would make this negative 2x minus 6 to be 0.
3.
3 would give us negative 6 minus 6.
Minus.
If I have negative 2x minus 6 is equal to 0, then negative 2x would be equal to 6, and then x would be equal to 6 divided by negative 2, which would be negative 3. Does that make sense?
Yeah.
Okay, so we have a 0 at x equals negative 2 and x equals negative 3. Okay, so finally, I mean, we can go ahead and graph this thing now. So we know we have horizontal asymptote at y equals negative 2. We know we're going to have a vertical asymptote at x equals 1.
And we'll have zeros.
And we're going to have zeros at negative 2 and negative 3. Which is troubling, actually. Why is that happening? Wait, that doesn't make any sense. Why is that happening? Wait, this looks like... How is that happening? One second here. So, okay, if we plug in negative 3, we'd get negative 2 times negative 3, which would be 6, and we subtract 6, we get 0 for sure. The second one, we plug in negative 2. Yeah, okay, so those should be our zeros. Okay. Well, then let's just carry on for the time being. It's probably happening because we have a double root at x minus 1. Okay, so let's check here x minus 1. Let's check what's going to happen. At x equals positive 1, n of x, the numerator, is going to be negative 2 minus 6 is negative 8. times negative 1 plus 2 is 1. And q of x is just equal to 1, which is equal to 1. So a is less than 0. And we know that the power of our denominator here, our root, is 2. So we have a less than 0 and an even power. So we go back to our setup here. If we have a less than 0 and an even power, we should be using the purple setup. So what does it look like? It looks like we have down and down on both sides. Okay, down and down on both sides. So our picture is going to look something like this. We know that here we're going to have down and we're going to have down. Okay. And if I were to venture a guess what this looks like, I would say it probably looks something like this. And then on the left side, it looks something like this.
Should have to cross the zeros on the line.
Correct. We know that it has to go through these 2 points. And we know that on the right-hand side, there's no zeros. So it definitely shouldn't be symmetric and look like this. Because otherwise we would know that there should be zeros here and here, but we know that there's no zeros there. So we know that the right-hand side should basically be going down here, and it should be going close to y equals negative 2 here, and it should not be getting anywhere close to this thing here. That's what we know about the right-hand side. And what we know about the left-hand side is basically that it's going down here. We know that it goes through those 2 points, and we know that at the end it gets really close to y equals negative 2. So as you can see, this kind of gives us like an incomplete picture. We just have that we have these green pieces of information, and we have to kind of guess a little bit about what's going on in between.
Yeah. Teacher, how did you find A? Can you repeat that step?
Sure. So, okay. We defined A to be equal to
nx over qx.
Correct. So here's what we said. If f of x, I need more space. We said that f of x is equal to n of x divided by x minus a to the power m times q of x. And we define this part to be our a. So we could rewrite this, for example, as 1 over x minus a to the power m times n of x over q of x. And we define a to be equal to n of a divided by q of a. Okay? So when we had, what did we have? Negative 2x minus 6, x plus 2. Divided by x squared. No, x minus 1 squared, right?
Yeah.
When we had this, we rewrote this as 1 over x minus 1 squared times negative 2x minus 6 times x plus 2 divided by 1. And then A would be equal to plug in A in for X in this region. So our A was +1. So we got -2 times 1 minus 6 times 1 plus 2. And we divide by 1. And that gave us -8 times 3 divided by 1 is -24. And we decided that that is less than 0.
That makes sense.
Mm-hmm. Yeah. And if you don't want to use this A business, what you could try to do is just take a value which is really, really close to 1, say 1.001. If you plug it into f of x, f of 1.0001, you would get something like -2 times 1.0001 minus 6 times 1.0001 plus 3 plus 2, right? And then all divided by, well, if we took 1 minus 1.001 minus 1, we'd get something like positive 0.0001 squared in the denominator. And if you evaluate this out, you will get a very large negative number. Okay, so if you don't like using the A trick, you can always just try plugging in a point which is very close to the asymptote and see what's going on with the function. If it's going really extremely negative, then you're going to draw a picture which looks like what we did, where the graph goes very far down, right? And then likewise, you could check something like 0.999 on the left-hand side, in which case you're going to get basically the same thing on the top, only the bottom will be something like, it would be something like negative 0.0001 squared. But if we take negative 0.0001 squared, we get the same thing, which is why we have the same behavior on the left-hand side as we have on the right-hand side, because the top is practically identical, and the bottom is going to be the same.
Yeah, good. Thanks, teacher.
Okay.
Okay.
Yeah, I actually have to go for another class right now.
I'm sorry.
So I'm gonna stop the recording. But if you want
to, office hour today. I'm sorry.
Okay, I don't have office hours today, but I have office hours on Monday and on Wednesday. And if you want to make a meeting, then send me an email and we can schedule another meeting to talk more about this. Okay?
Thanks, teacher.
Yep, no problem. Have a good day.